Bismillahirrahmanirrahim. Lec-3A thermal equation of the state, and today we'll be talking about the non-ideal thermal equation of the state, and in a later lecture we'll be talking about the tabular form of the properties of the substance of property of the pure substance. So in the last lecture we had ideal thermal equation of the state. But ideal gas law itself is not a good predictor of PVT behavior when we are talking about the gases and which are the gases which are at the high enough density. So when we have got the gases at the high density, there is some molecular interaction forces between them, and when we have got the molecular interaction between them, there is the behavior, let's say a behavior between pressure and volume that is definitely not the same, and that is behaving like deviating from the Boyle's law. So this happen, and this normally happen near the vapor dome. Again, if we have got a high temperature, so that high temperature induces the molecular dissociation. And when we are talking about the molecular dissociation, let's say for example talking about the nitrogen, and we are talking about the nitrogen and nitrogen as a diatomic nitrogen. So if it dissociate, that means like it will be an monatomic particle, and obviously the monatomic nitrogen behavior will not be same as the diatomic particle. So obviously there would be some difference in the behavior of those gases. So the alternative approach towards the predicting the non-ideal the behavior of the gases, or what we say like the real behavior of the real gases, we have got some corrected thermal equation of the state, and we are talking about the equation of the state now. The first equation of the state is the van der Waals equation, and it is again the same equation of the state of the fluid composed of particles that have got the non-zero volume, and there is some pairwise attraction forces between the particles. Um, Make sure like when we are talking about the ideal, we are not talking about the attractive or repulsive forces between the particles. It was derived by van der Waals in 1873 and got a Nobel Prize in 1910 for his work on the equation of the state for the gases and liquid. This equation itself is the based on the modification of the ideal gas law, and it approximates the behavior of the real gas. So make sure again we have got the word approximate, but yes, we are talking about the real fluid right now. As I said, like when we are talking about the pairwise attraction forces or repulsion forces between the particles, so we are deviating from the Boyle's law. So that means like behavior will be not like this, or the pressure would not be proportional to 1 over V. So we are talking about the change in pressure with respect to different change in pressure, different change in volume with respect to pressure. So that will be non-ideal. So it is actually the modification of the ideal gas. So obviously the behavior of the pressure and volume is different now. So the the van der Waals equation is something like this. So P is equal to RT by V minus B minus A by V square. So in that case, A and B are the variables we need to be calculated. But make sure, like, let's check this one. We have got TC right now in this equation, and we have got the PC right now in the equation. That means that we have got the critical temperature and critical pressure. So in the above statement, we say like when we are talking about the behavior near the vapor dome, if I'm saying like near the critical point, so we are talking about the non-ideal behavior. So now the van der Waals equation, now it can approximate the behavior of the real gases near the vapor dome or near the critical point. The next modification of the ideal gas is the Redlich-Kwong equation. Again, Redlich-Kwong equation is the empirical and algebraic equation that relate between the temperature, pressure, and volume. But it is generally more accurate than the van der Waals equation, and that is near the above the of the ideal gas equation, and that is above the critical temperature. It was formulated by the Redlich and Joseph Kong in 1949. Uh, Again, it is undergone many revision, many modification in either to improve its accuracy or in either to have a better simulating condition near the lower temperature, or you're talking about the lower temperature, which is actually near the vapor liquid equilibrium, or talking about the including the vapor liquid equilibrium as well. Again, we have got the equation which is equal to PV by RT by V minus B minus A something. Um, if you can check the equation from above or compare the equation with the van der Waal, it's a little bit getting more complicated now. So just having said that, we're just saying like um, Redlich-Kong equation is more, say like complex than the van der Waal equation, but it is more accurate than the van der Waal equation. So that means like if we are talking about more accuracy towards the real gases, we will be talking about more complexity in the equation. So the simplest equation is equal to PV is equal to RT. Sorry for that. So PV is equal to RT. That means like if we are talking about the simple equation, we are talking about the ideal condition, condition which means we would be having some constraint on it. But if you are talking about the more accuracy, so we would be talking about the more complexity in equation. Now, talking about another method rather than the thermal equation of the state, and that is the compressibility factor. Uh, Going back towards the ideal gas equation again. So ideal gas equation PV is equal to RT. So that means like it is would be predicting the ideality of the gases. But let me modify this equation a little bit more, and that is PV is equal to ZRT. So that means like if the value of Z is 1, so we are talking about the behavior which is ideal behavior. But if the value of the equation Z is greater than 1 or Z is less than 1, so that means like it will be deviating from the ideal gas or ideal behavior. So Z, if I say like Z is equal to PV by RT, so this is what we call it as the compressibility factor. So compressibility factor is deviation from the ideality of the gases measured by Z is equal to PV by RT. Uh, we will be looking at the compressibility chart, and we will be looking at the nitrogen compressibility chart to understand this compressibility factor. Uh, so the plot is the graph is plotted between the Z, which is Z is equal to PV by RT, and pressure is changing from this direction, and this is the compressibility chart of the nitrogen. We are talking about the different pressure, and we're talking about the different temperature. So we have got the increasing temperature from this direction to this direction, and we are having a increasing pressure from in this direction. Z would be equal to 1 on this line, and Z would be less than 1 if you are talking about the this direction, and Z would be greater than 1 if you are talking about this direction. So let's have a look at any of the conditions. So let's say a condition which say like if we are approaching towards zero pressure. So for all the temperature, if I'm talking about all the temperature lines, if you can check these lines as well. So if my pressure P is approaching towards 1, so that means like my Z is approaching towards 1 as well. So in that case, if I'm saying like if the pressure is minimum, Z would be approaching towards 1, or the behavior of the gases would be ideal. Now let's have another example. Let's say and let's say like if I'm let's have a pressure above the critical point, and let's have a pressure with at 10 megapascal, but the temperature, if having increased pressure, but also the temperature is increased, that mean like increase then 300 Kelvin. So that mean like even if my pressure is increased, but my temperature is also increased or more than 300 degrees centigrade. So you can imagine like this line is approaching towards 1 now. So for that mean if the temperature is greater than 300, Z would be approaching towards 1 even if the pressure is but sorry, keeping the pressure less than 10 megapascal but still above the critical point. So that means like the behavior will be still ideal if you're talking about the high pressure, high temperature, and sorry, the if you're talking about the high pressure and we are talking about the high temperature, the behavior will be still ideal. Now let's say hold uh, pressure at 4 megapascal. So we are talking about a pressure which is somewhere near vapor dome, let's say. But let's say decrease the temperature. So having a pressure of 4 megapascal, but the temperature is actually lower than 300 Kelvin, or getting the temperature lower than 300 Kelvin now. So if I'm saying like now the Z would be less than 1 now. So that means like if I'm having a pressure of 400 megapascal near somewhere vapor critical point, and the temperature is less than 300 Kelvin, so Z would be less than 1. So in that case, if I'm saying like Z is equal to PV by RT, remember like V is equal to volume per unit mass. So that means like mass per unit volume is density. So that means P would be equal to rho RT. So that give us a relationship between the compressibility factor Z and the density. So in from this thing, it's a like if Z is lower, getting lower, so that means like the density would be increasing. So if density is increasing, so ultimately it's say like if there would be some attractive forces between the molecule, so that would increase the density. So if I'm decreasing the compressibility factor, it will increase the density by attracting, or by the molecule which would be attracting itself. Now, let's say if I'm talking about the pressure, which is let's say above the 30 megapascal, somewhere near 30 megapascal. So let's say for all the temperature right now, because if you can check it, like all the temperature lines are moving upward. So for all the temperature, uh, if I'm increasing the pressure for all the temperature lines, or for the all the temperature, Z is greater than 1 now. So you can imagine like now we are talking about this thing now, so Z is greater than 1. If Z is greater than 1, so there would be pairwise repulsive forces between the particles. So if you say like if you are still applying a pressure on the gases will be actually repelling each other. So when you are they're repelling each other, so that mean like the pressure would be greater, the change in volume would be less. So there would be difference in P and V now. So this is the generalized compressibility chart, can be developed by the generalized gases. But for the specific, you can imagine like this was the specific one.